All right, so your written test number 2 will be next Wednesday, WSC, the same place. Please watch out for the start time and etc. You definitely need your mobile phone for dual mobile verification, like last time. You can look at the guide, you can look at the practice question. I still need to find out that review session, but I will definitely release that if give you the link if I can find it. Most likely I can. And also lab 3 solution, please try it out a little bit more, and I will also give you the solution tomorrow before the submission deadline. So you can combine that together with your study for written test number 2. Okay. All right, any questions? Yes?
So I just want to repeat in last lecture, today's content, the last lecture content will be in the written exam.
That's correct. So I think at the end of today, maybe right before I end the class, I'll tell you guys exactly the slide number you got to study up to. I'll do one confirmation in the class. I'll also write out to everybody in the e-class to say which slide.
Thank you.
Yeah, okay. But I pretty much know what I need to end today, but we'll see how that goes. All right, let's do a quick recap about Tuesday.
Excuse me, someone else
Yeah.
has a question. Someone else has a question.
Oh, go ahead.
Will we be doing a review session?
I think at this time I may not be able to. However, I would say maybe try to see if we can drop by Monday's office hour. I can definitely give you guys priority on Monday, so if you got any questions. I cannot really commit, but I might be able to host some maybe a Zoom office hour, maybe over the weekend.
Okay.
May not be very pleasant for you, but if you need it, I'll try. I'll see. I cannot commit. I don't know. I gotta check my schedule. Okay, yeah. May not be a review session, at least I can get office hour, you can ask questions, at least, right? Okay, yeah. All right, let's now do a quick recap, okay? And then we'll move on with refinement number 1. So last time, we actually revisit this first attempt for initial model M0. We said that when we try to prove about deadlock freedom, from this particular sequence here, we can either do EQLR or EQRL. And then from each of these, we will be able to arrive 2 different unprovable sequence. One of them will be n larger than 0. The other one will be d larger than 0. So these are both mathematically valid unprovable sequence you might arrive by applying different inference rule. However, we have to judge which one we want to use to go back to the original model and fix it, right? That's something we kind of talked about last time. And we kind of did a justification, and this one here doesn't seem to be realistic. You cannot say the number of cars in the island compound bridge, the island bridge compound should always be greater than 0. It could be 0, right? It's definitely possible, right? We talk about it, so please review it. And then we also talk about if you go for this particular unprovable sequence, how can we interpret that and go back to the original model and fix it? And once we fix the model, we will be able to regenerate the proof obligation. So you want to make sure for written test number 2, you should be able to know how to apply the inference rule. And also, if I ask you about a particular proof obligation, you should know how to generate the sequence accordingly, right? So I think written test number 2 is also very relevant to your ultimate exam as well. Okay, I'll talk more about your exam maybe in the last class or second last class. Okay, I'll give you guys some tips as well. All right, so we have this additional axiom, so that will be added as one additional hypothesis. And then eventually we will be able to prove it, right? Can go over the proof. I would suggest really try with this one here. I left one clean page for you. Download it and give a try. I think just make sure. And maybe you want to even get rid of all these. You don't want to kind of remind yourself exactly what you can use. You may not have that log string, during the exam or test. You want to really just get those 2 pages are made available on the lecture site. Only given those, how do you select the appropriate ones to really discharge the proof sequence rather than relying on this particular short list. I mean, it may not be available to you all the time. And then we spoke about the summary about the initial model. So we have done this particular change for deadlock freedom. We have done these 2 changes to the guards for invariant preservation. Okay. And then we talk about the first refinements. You just have to understand at the conceptual level, we are going from island bridge compound, split them into the bridge and also the island, right? So now in this new, more concrete perception about the system, we're actually trying to use A, B, and C to specify the measurement. You can think about eventually somehow A, B, and C might be somehow measured by some sensors or actuators, right? That's something you might be subject to refinement. But at this point, we don't have to worry about exactly we got those numbers. It's not important at this level. And then we spoke about here, about, right, abstract versus concrete, and also old versus new. Right? Just get used to the terminology. So if I mention any of these in the test question or exam question, you want to be able to tell exactly what I meant right away. Right? You don't want to waste any time deciding what I'm trying to say. And every time we talk about abstract versus concrete, it's always like a relative. So there is, well, except for the very, very first model, you can say that's the most abstract one. Other than that, every time if you talk about a pair of models, you can always say which one is actually more abstract and which one is more concrete. Okay. And then we talk about, that's the last part we did last time. So we spoke about the different variables A, B, and C, right? A here, B here, and C here, right? And then we talk about typing invariants. All of them should be natural number, larger than or equal to 0. And invariant number 4 is something we call linking or gluing invariance. It is a way to really relate the variables from the abstract and the variables in the concrete. We are trying to relate the n from M0 and A, B, and C from M1, right? We're just trying to do some relation. It's going to help us a lot when we see the first example today about this, designing the guard for the events in the M1. The invariant number 15 is about safety invariance. We want to make sure the bridge is one way and also never get a chance to really clash between the cars. So that's something we ended up having, which would be A equals 0 or C equals 0. Right? So we talk about other alternatives as well, contributed by your fellow students. You can also refer to the recording for the details. Guys, any question from Tuesday? All good? Okay. So now, I would like to talk about the events. Specifically, I want to talk about, okay, so here just repetition of the axiom and also invariant, right? So this is the invariance that we just spoke about here. Given all these, so now we are going to figure out the design for ML out and also ML in, right? These two events. Let's figure out, and also they do require a little bit of derivation logically. So let's go over that maybe carefully. Let's look at right here. Okay, let's look at right here. So we talk about abstract state machine. So this is something we just said earlier. And then we want to see under what circumstances should the event be enabled. That's something we want to design. So we actually got ML out, all right, right here. Okay, so here, let me just talk about what ML out really means right here. You can think about here, ML out is the events. Let me just do this one here. Okay, let's first of all talk about ML out. Okay, that's the first events. ML out is this event right here. That means there is a car going from the mainland off to the bridge. But we want to make sure they will do this only when it is safe. There's no concern about clashing with another car, maybe coming back to the island, coming to the mainland, right? So that's why this one, you can see the event here, action is actually quite straightforward. Because we are basically +1 to the A measure right here, right? So that's what the ML out will do. So that one there, I don't need to bother you. I just give it out to you directly. So we should just increment the A value just by 1. So that means there's one more car on the bridge that's going towards the island. But now, the important thing is, under what circumstances should ML out be enabled? Okay, that's the question. Okay, so let's look at the slides for some hints, and then we'll talk about exactly how that can be programmed. Designed, can be formulated. Okay, so the first one here, the bridge's current traffic flows to the island. That means there is no car going from the bridge back to the mainland. So what I'm saying is, we know ML out is really going for this direction. In order for this event to be safe, you want to make sure there is no traffic going this way, right? Obviously, okay? For that one there, it's easy. What should that be? C equals 0? Yeah, exactly, because C here measures about the traffic from this way. Exactly, right? So that one there, we can write it out directly, okay? So let me say that's guard number 1 right here. I can simply say C equals 0. Okay, this one is going to be used as well. So let's assume we got this one here already. Okay, that one there is not too much confusion, so I'll leave it here. All right, the second one. The second one there, I leave it a little bit vague, but conceptually that's correct. The number of cards on both the breach and the island should be limited. Okay, what I'm saying is, right here, when I try to do ML out, I'm basically changing this value here. However, if you recall back to N0, we say that for the island breach compound over here, there is a value called N, right? And we also got one guard for ML out, if you remember, right? That's something I want to refer to it right away, and I'll show you how we can draw the connection. So when you study for this one here, I want you to go back to the abstract version for the ML out right here. That one there was saying that whenever we want to increment a value for n, which is the abstract variable, we want to make sure n should be strictly less than the cap currently. Strictly less than. Okay, let's now put it down first. And then I'll visualize a little bit for you. Okay, so number 1 here. So let me just do another derivation. Okay. Let me say A here. Okay. So here from M0, the abstract guard of ML out is n should be strictly less than d. So this one tells us how limited should n be. And now, how can we use this as a basis to work out what should be the consistent behavior in the refinements, right? Visually, let's think about it this way. Think about what we have back in M0 is right here. This is the island breach compound right here. And that one there we say n should be strictly less than d, right? Before we didn't have this like a split between the island and the breach. So that's now we have it. We want to make sure right now this one here can be reflected in terms of A, B, and C. Question? Yeah, or yeah.
So, since we wrote the guard C equals 0, I'm assuming you would just become A plus B is less than B?
Yeah, actually your result is exactly right. So I think I can see your justification there as well. So let's write it down. I think you're exactly right. So your fellow student actually definitely on the right track. So the main thing I want you guys to grasp is we want the basis for this concrete guard does not just come out of blue, not really. It comes from the abstract guard that we had earlier. Okay, so now let's see how we can help. So n here is a abstract variable, and we do have the linking invariant here to connect the two words. So here, invariant 1, 4. All right, so that's a linking invariance. So the linking invariance tells us that A plus B plus C should be equal to n. All right, that's what we know. And we have a special case for here, this ML out, because C, we just agree, it should be 0 to make sure there's no clash. All right, so now I'm going to put part C as well. We know that the concrete guard that we just had would be C equals 0. Let's put all these together. All right, I'm going to put it here. So if I got the A here, which is n less than d. And also I got B here, which is, let me write better, B here, which is A plus B plus C equals n. And also I got C here, which is C equals 0. Right? When I put all these together, let's see what we have. All these together, you can think about C here is going to be just 0. So that means A plus B equals n. n can be replaced by a plus b. So we got a plus b less than d. That's exactly what you suggested, right? We're just trying to make it very explicit for everybody. Good. So the second guard we're going to have will be a plus b less than d. Right? So that's what you will see on the slides. But I think it's more valuable for you to actually see how we derive these two guards. That's more important. Okay? The lesson that we are learning from here is whenever you're trying to put some guards in a concrete version of the event, you always have to take as a basis an abstract version and go from there. There might be certain invariant condition you can actually use to do some substitution. Okay. Good? Okay. All right, let's talk about MLN. MLN is a bit symmetric because you can see right here, MLN is right here. It is actually going from the bridge back to the mainland right here. But in some way, this one is a little bit more straightforward. This one, you're just going to make sure there's at least one car in the bridge so they can go back. If there's no car on the bridge, MLN will not be enabled. Right? MLN is just about car going back to the mainland. So if you see on the slides right here, there's at least one car heading there. All right? So any suggestion here? It's just one guard. Yeah, I agree. So let's say here, so for MLN, so let's now put it, okay? And then I'm going to give you guys one question to think about. Oh, I'll do that. Good. MLN. So the guard we're going to add will be just one. C larger than 0. So that means over here, there is at least one car right here that's going back. So that when we decrement the counter, we are not going to decrement, for example, 0 back to, down to -1, which is going to violate the fact that C is a natural number, right? So we know that C here is going to be decremented whenever we're trying to do MLN. So we got to make sure it's at least larger than 0. Question for you, all right? So here, because the traffic is really going this way, when we say going for MLN, right, let's say this way, is it necessary to make sure there is no traffic going this way at the same time? All right, you might be thinking, right? Okay, why don't we ask the following question? I'll put it down and then you guys tell me intuitively. Here's the question. Is it necessary to add a guard, which is, since we are trying to go this way, we want to make sure this way A is 0. So when I say necessary, I'm already admitting adding this guard is not going to hurt. Conceptually, I believe that's correct. However, is it really necessary? Necessary in the sense that maybe somehow A equals 0 is something already like a theorem. It's derivable from what we have already got. Yeah?
Yeah, I think it's not necessary because before the action takes place, that we already have invariant 1,5, either A equals 0 or C equals 0. So the first guy, C larger than 0, already implied that A equals 0. So we are fine.
You're definitely on the right track. Definitely on the right track. So guys, I think that this one here does require a little bit exercise here. So what I will do is I'm going to put this question, I'm going to formulate this question here as a sequence. If you can prove that sequence, it tells that it's not necessary. Okay, I'll put it down here. Okay. So what I will do is I'm going to put something here. So first of all, I'm going to put C larger than 0. So this is the guard that we just introduced. Okay, one of them. Another one I got, as you fellow students said, we got this safety invariance right here, invariant 1,5, okay, which is A equals 0 or C equals 0. So that's invariant 1,5. We are basically asking, given these two as hypotheses, can we somehow show that A equals 0 is provable? That's what we're asking. So if I box this as a sequence, This will be a very relevant exercise for you for next Wednesday. All right? So I'm going to put a star here. Put it here. If this sequence is provable, then A equals 0 is not necessary because it's simply entailed from what we already have. I will give you a little bit hints. Okay, that's also relevant to next Wednesday. Okay, what kind of inference rule do you think you want to use as a first step? Monotonicity may not be so applicable in this case because I think we do need both hypotheses. So what we have here is a disjunctive hypothesis. Did we learn any inference rule to somehow deal with a hypothesis that's a disjunction? I think we did, right?
Was it R1?
The R1, R2 are when the disjunction is on the go. All right, be careful. Okay, yeah. Okay, anyway, so that's something you got to review, but I'll give you hints. Look at ORL. Because in this case, you can think about, well, I'm arranging the sequence vertically, but you can see the disjunction here happened to the left, like a hypothesis, right? Think about how you can deal with that. You may have to split this into two sequences instead. And then it will be quite straightforward to really discharge each one of them. All right, so think about if you're able to prove this one here, then you don't need to add A equals 0. If you're not able to prove it, you better add it. It's a safety guard. All right, questions? All good? Okay. Let's now move on. I hope that's clear. Let's clarify maybe just a few more things, and then we should really move on to something called guard strengthening. Okay, I think that's the only concept I want to talk about. But just before that, let's do a few things. Okay. Okay. So let me just see. Okay, we are now done with this. Okay, I think for the next few slides, I'll just use the iPad notes. You know, it's a bit easier and more efficient to go through. Okay, let's now go on for transitions. Okay, and then this one here, this one here. Okay, got it. Okay, let's talk about just transitions. I want to show to you visually about how you can relate the two kinds of transitions. Let's take a look at that first. Okay. So now we have two models. We have the abstract model, which is M0. And we have the concrete model, that is M1. Okay, we got two models over here, M0 and M1. And we're trying to do transitions. Okay. The way to do it is we're going to put the two models or two abstract machines side by side. So thinking this way, each state for M0 is going to look like something like this. We only got M variable to worry about. Each state in the M1 has A, B, and C to worry about. And let's say for this particular example, let's say D is simply equal to 2. Maximum 2 cards, let's say, maximum. Okay. So what I want to do is, let's say init. So let me just copy that. So this will be the initial states for M0. Okay, I'll put it right here. Okay, and this will be the initial states for M1. Okay, right here. Put it side by side. So think about this. Let's do the abstract one first. So what we have is after initialization, we know that n should be equal to 0. Right, from the init event. That one's easy. And also, after initialization for the concrete road, we haven't really shown you that, but that one just initialized A, B, and C just to 0 as well. Okay, that one you can take my words for that. 0, 0, 0. How do we relate these two states together? All right. So first of all, let me make some annotation. First of all. So think about this one here is the abstract initial states. And this one here is the concrete initial states. Okay, one is abstract, one is concrete. But how do we make sure they are consistent with each other? You have to look at all the invariants that's to do with linking them together. At this point, we only got one single linking invariance, which is invariant 1, 4, right here. So what I will do is I'm going to somehow try to link these two states together. They're related, and then they're related by just one single invariance. Invariance 1, 4, which is, in that case, A plus B plus C, 0 plus 0 plus 0 equals N, 0. That one trivially true. So in the beginning, the initial states for abstract and concrete are related to each other by the linking invariance. So that's good. Okay? Let's just do one single transition just to give you the idea. And I'll give you a little bit of exercise to try it out as well. Okay? Let's say we want to consider a trace like this. Let's say after the trace, here, let's say we got init already. Let's say we try to do ML out. Okay? Just do ML out. If I try that, let's say for the abstract events, I'm going to try ML out right here. Okay? ML out. And the other one there, I'm also going to do ML out, the corresponding version, like a concrete version. ML out. Okay, like that. And let's now just put the two states as well, the post states for both of them. Okay, one here. And also one here. All right. According to the abstract version of the events, you can see if that one's ML out, it's going to plus 1 to N. So 0 to just 1 right here. And then the other one, for the ML out right here, is going to increment just A. So that means A will become just 1. B and C remain to be 0, like that. Right? Trivial. Okay? And then is this post states here consistent between the two words? I'm pretty sure you can justify that. That one there, if you try to link them again just by the same invariance. So here, invariance 1, 4. So here, 1 plus 0 plus 0. Is it equal to 1? Indeed. So that one holds again. Right? So you can think about conceptually, so this is kind of the parallel state transition we're doing between the two words. You got to make sure for each corresponding states, the linking invariant should really hold to relate them together. Guys, are we okay with this? Okay? Yeah, I just want to make sure. Yeah, I take silence as yes. Okay. All right, and then exercise for you. Here, at the moment, can we actually do ML in to continue with one more transition? That's a question. But we're going to revisit this a little bit later. All right, think about that. Okay, I'll put a question mark. But I think the main lesson for you to learn from this page here, just to see intuitively how you can relate the abstract and the concrete states. That's the main lesson. Okay. If that's okay, let me move on. All right, let's now clarify some terms very quickly. Okay, before, after predicates. Okay, so for that one there, so this one here. Again, let's now talk about, let's say, for MLN. So this one here is a concrete events, concrete version. So concrete events. And if you recall, in the concrete events, we actually got A, B, and C, right? So we got A, B, and C. So now when you actually see the event action right here, you will see C becomes C minus 1, right? So now the question is, what should be the before-after predicates? You might be thinking, well, according to what we learned earlier, it might just be C prime equals C minus 1. That's only partially correct, but not complete. You got to make sure You only put actions about what should be changed. Implicitly, anything that's not mentioned here, be it like A and B, they simply remain the same as before. Okay, so what I should really remember is, because this will be necessary later for the proof, you can think about implicitly there's a conjunction here, and A prime equals A. Also, B prime equals B. Okay? So the before-after predicate for this action here is actually 1, 2, and 3. And these two are simply implicit, meaning that we are only modifying the variable C. But for A and B, we simply don't touch them. But I got to put it here because that will be important later on if you want to do any substitution. So it's complete for you. Okay? Okay, quick exercise we can see right away. How about this one here, right? That one there, for sure, you actually got A prime equals A plus 1. But implicitly, B and C are not mentioned. So they should remain unchanged. So B prime equals B, and also C prime equals C, right here. Okay, straightforward, okay? But if you really got a question, please just stop me, okay? Yeah, please.
We also apply n prime equals n.
Good question here. The answer is no. Your fellow student question goes like this. As part of, let's say, as part of this before-after predicate here, should we also add to say n prime equals n, or something like that? First of all, when you say n prime equals n, that's not correct. Because if you recall, what happened back in ML out, right? We actually say n prime equals n plus 1. Right? If you go back to the abstract version for that events. But the more important thing is, since here we're talking about the concrete events, we don't really change the n. So they are separate scope for the variables. So you shouldn't even mention that. Okay? I'll make it as a note. So this one here, no, because n is an abstract variable. So you don't mention that, since we're talking about concrete events, right? Good. Okay, and then let's see, right here, I think this one here, just some, yeah, okay, some very quick link. N here is the abstract variable. A, B, and C are the concrete variable. And the way they are linked is by the linking invariance. Okay, just to do a little bit more connection, right? That's how they are linked. Okay, and then it's also going to be useful for later. When you talk about the guards for the abstract event, you call it an abstract guard. Okay, that's something we'll use later. So these two, that's specified in terms of the abstract variable n, they are called the abstract guard. And these two right here, oh, sorry, these two, that's specified in terms of the concrete variable A, B, and C. They're called a concrete guard. Okay, like that. Okay, just Diego.
Sorry, quick question. So you're able to use the linking invariant because these two machines share the same context, right? That's how n can be seen in both machines.
Well, put it another way, you can think about somehow when we try to design M0, we cannot refer to A, B, or C, right? It's more, a little bit like an inheritance. In the parent class, you don't really see the variable in the child class, but not the other way around. In the child class, you got inherited all the variables from the parents. So that's why in this case, you are able to use the invariance to refer to A, B, and C, and also N, which is somehow in the abstract model.
Okay, so we're able to reference n because we know, as a matter of fact, that M1
Yeah.
it's a refinement.
Yeah, yes. And also, you're quite right. Both of these machines, they share the same context. Yes, number one, okay? But how about the variables? In Rodent, which we don't really cover, we didn't let you do it. If you want to do this in Rodent, you got to declare M1 refines M0. That way, it automatically tells you that n is visible at M1, right? That's something I didn't really say. Yeah, good. All right. All right, guys, one more page that could be a little bit boring, but I'll try to go as clearly and also as efficiently as possible just to say some formal components. Once we have introduced these formal components like before, we will be able to talk about guard strengthening. Okay, let's do it quick, but carefully. And then after that, we'll take a short break. Okay. For that one, you can see that's on slides. Let me tell you the slide number. So we finished talking about before, after predicate, abstract versus concrete. And also right here, okay, it's basically from slide 50 onwards, maybe about 2 or 3 slides. Let's talk about it quickly. Just about the different terms that we have to know, okay? Let's start with something obvious. So we got basically V and V prime. So these are the abstract variable, okay? So these are the abstract variables. Versus whenever you see W and W prime, they refer to the concrete variables. So whenever you see like a V, that means abstract. You see W, that means concrete in the proof obligation rule. We'll see that right after the break. Okay? So example. So in our case, you can think about right here, the V will just be the list of the abstract variable, which is just N, just right here. All right? And also V prime will just be the post-state value N prime. Okay? And for the concrete variables, it should be A, B, and C. That should be the list. We got A, B, and C. And W prime will be the prime version. A prime, B prime, and C prime, right? For our model. Okay? That's about abstract versus concrete variables. And then we got abstract invariance versus concrete invariance. Okay? So just to start with, you can see abstract invariance, which refer to these two. They are in the invariance in the abstract model. And also we got concrete invariance, which are the invariants right here, all of them, right here. Okay? Let me just list them first, and then I'll talk about what's really inside. Okay? So what we have, for example, here. So abstract invariant, which is I. And then we're going to refer to, okay, let me just talk about it. It's going to be constant, which would be the D. And also the abstract variable, which will be N. The abstract invariance can only refer to the variable, the abstract variable, and also constant. So that would be just invariance 0, 1, and also invariance 0, 2, right? 2 invariants. Similarly, when we talk about J, whenever you see J in the proof obligation, it talks about concrete invariance. And for the concrete invariance, you can see that we also refer to C, the constant, and also it makes sense we refer to concrete variable. But notice that we can also refer to abstract variable. Because linking invariant, for example, right? You got to refer to both variables. Okay? You can see this is, these are the concrete variables. And this one here is the abstract variable. We can refer to both, right? So here we got the constant D, and also abstract variable N, concrete variable A, B, and C. And then it's just going to be all these. Invariant 1 to 5. Okay, I'll just put one of them. Invariant 1, all the way to invariant 1, 5. Okay, 5 of them. Okay, just a list by the labels. All right, very quick. These, also very important. The G here is about abstract guard. G here is about the abstract guard. And the H over here is about the concrete guard. And of course, every time you talk about G or H, it's kind of specific to a particular event. Let's make it explicit. So think about in terms of ML out and also ML out right here. For example, we got 2 versions over here, right? So if you try to look at these 2, okay, right here. This is the abstract guard, n less than d. So I'm just going to put the G abstract guard, and you can refer to the constant d, and also you can refer to the variable n. And in this case, you can say it is of ML out. That one is simply n less than d. It's only a single guard. If you got multiple guards, like a multiple line, you got a list of multiple items there. Okay. Similarly, so now here we got concrete guard, which is H. Okay. H over here, you can refer to constant and also concrete variable. So D here, and concrete variable will be A, B, and C. And that one there should be for ML out. Now, how many do we have? We have one here and also one here, right? The thing we just did earlier, just right the first thing today. That one there is going to be two things. A plus B less than D, and also C equals 0. Two guards, 1 and 2. All right. So you can definitely define accordingly the G and H for MLN. I'll leave that to you. You can also see that on the slides. Okay. All right, final thing, just about, we talked about E before, which is about the effects for the events. So E here is about abstract events effect. For example, you can see n plus 1, right? So that one there is really the effects, and then of constant D, variable n, of ML out, right? Just this single one, n plus 1. Okay, you can see the complete definition in the slides as well. Finally, we can also refer to the effects for a concrete events. Let's say accordingly, we got A plus 1 right here. So that one there is going to be the effects of, we can refer to constant and concrete variable. Constant and also concrete variable, A, B, and C of ML out. Okay, right here. Okay. The main thing we're going to see later is just about this G and H, about abstract guard and concrete guard. So after we take the break, we'll try to apply many of these just to see how we can understand guard strengthening. Okay? Question?
Yes, I was curiosity, how are you going to prove the invariant conservation in model 1 after you got so many, you need to refer to...
It's a very good question. So I would say, it's really hard to put in a single sentence exactly how we're going to do it, but we definitely have to put invariant from both models all together and formulate it. Good news is we're not going to cover that in the written test too, okay. Right? So we're going to do that properly maybe next Tuesday.
So simple question,
yeah.
Do we have to prove the invariant for both this model and the last model?
Say it again, what do you mean?
So when we have to do an invariant preservation for the refined model, do we have to prove the invariant for both this model and the model being refined?
Think about what we did earlier. When we actually talk about M0, we already proved about invariant preservation for M0. So that one there, we don't need to reprove it.
Okay.
Right? But we somehow have to show that given the new invariant that we have, well, concrete one, we somehow want to show those invariants are somehow consistent with the old invariants to some extent.
Okay.
But we'll get there. So, yeah. Right, guys, why don't we take a short break and then we'll come back for guard strengthening. Okay. So I'm going to start talking about guard strengthening. That's the only thing I want to talk about today. I'll make sure I explain the basic concept and also intuition clearly. So there are in total 2 proof obligations that has to be discharged for guard strengthening. We'll see if we can get into it. If no, all the proofs are already there. But I would suggest you can take a look at the proof if we don't get a chance to get there. Maybe on Tuesday, I know it's before the test, but I can still go over the proof with you. But I already tell you, you should really study the proof over the weekend. Okay, we'll see. But at least the concept, I'm going to explain them clearly to you. All right, so that's the components we just spoke about before the break. Okay, now, when you study, for this particular slide, okay, for slide number 53, you don't have to worry about the invariant preservation part. You don't have to. That's something we have to talk about in detail on Tuesday. For this part, you don't have to worry for the written test. However, invariant preservation for M0, that one you have to worry, right? It's different. This one is more about invariant preservation for refinement. You don't have to. But for invariant preservation in a single model M0, you have to, right? Just be clear. Okay, guard strengthening. Okay, let's now start with that. Okay, before that, I want to clarify some quick idea. Because the guard strengthening, again, you can see guard strengthening, right? It's a special term. Now, we're going to talk about stronger versus weaker. I need to actually clarify that first before we can even talk about it. All right? Let's now get some notes done. Okay, right here. Let's now go back to our predicate discussion. Okay? Now, I need to explain when we talk about predicates. We have the notion about predicate being weaker versus stronger. Okay? So, principle is simple. If you're given two predicates P and Q, if you're able to show that P implies Q, if you're able to prove it, then we say the following. The antecedent P is stronger. Okay, let me write a little bit better, sorry. We say that antecedent P is stronger than the consequent Q. Symmetrically, we say that the consequent Q is weaker than the antecedent P. Both are equivalent same. All right? So let me give you one example and then visualize this a little bit. It's actually not too bad about the intuition behind these two, but I just got to visualize it. Let's now talk about P and Q. Okay? So let's say we got P in terms of X will be is defined as X larger than 0. If X larger than 0 is true, then P of X is true. Otherwise, it's false. Okay? We got another one, Q of X. X larger than or equal to 0. Right? Very similar. Right? You can see somehow this predicate will be true by allowing X be equal to 0. Right? However, this predicate here, when X is exactly equal to 0, is it going to be true? Not really. Right? So that's kind of there's a difference there. Right? But they are closely related. Okay? So you can try to convince yourself the following. So now in this case, P of X implies Q of X is the case. But when you say Q of X implies P of X, it is not the case. Because you can find at least one case, that can show as a witness. I'll show you that. Okay? How do we visualize the whole story? Okay, let's now see this. Right here. Okay? The way to visualize it is to think about for every predicate, think about what would be the set of satisfying values for that particular predicate. For example, in this case, think about the set of X that's going to make P true. Also, this predicate here, think about all the set of X value that's going to make Q true as well. Think about which set is larger and which set is smaller, basically. So let's now define that in terms of set comprehension. Okay? So what we have is we got the set X such that P of X is actually true. Also, we got the set X such that Q of X is true. Now the question is, which set is larger? Is this set larger or this set is larger? This one is larger, right? Well, obviously, as I hinted earlier, because this will allow X being 0, right? Exactly the point. So as long as you can actually put a subset relation right here, as long as you put a subset, then In this way, you can actually visualize it. Okay, I'll show you too. So this is what we said, the stronger predicates. And this is what we said, the weaker predicates, right here. Right here. Okay, let's now visualize it. So what we have is, let's start with, right here. This one here is going to be this, right? It's going to be strictly larger than 0. That means starting from 1, and then 2, and then 3, all the way to maybe plus infinity. Does not include 0, right? The next one is actually strictly larger, as long as you're able to show that. That one there, okay? You got, conceptually, just one value here, okay? So here is really the Q of x. And this one here is the P of x. And the 0 over here is something that does not satisfy P of x, but it satisfies Q of x. Okay? So now think about why we said Q of x is actually weaker, because it allows more value to be included. So somehow, think about predicates more like a filtering values that can be included into the set. If it's weaker, that means the filter is weaker, so you can allow more values in. Okay? That's how I thought about it. So this Q of x right here is weaker predicates because it allows more values to be included. And this one here is a stronger predicates. Stronger predicates because it filters more values. Specifically, it filters out 0. That's actually allowed by Q of x. All right? Quick recap. Whenever you have two predicates, if you're able to show that P implies Q is the case, then you say that this is stronger, meaning that it's able to filter out more values, and Q is weaker because it can allow more values than P can allow. Right? Think about that notion there, weaker and stronger. Just to help you, okay? Weaker and stronger are more relative. Let's talk about absolute. What would be the weakest predicate? Meaning that the predicate that's going to allow all values, basically. Any value can satisfy it. Well, that's a big hint already. True. Yeah, exactly. Because if you think about all the x where it simply got true, it's going to be a set containing everything, like a universal set, right? Symmetrically, the strongest set, which is going to be the strongest in terms of its filtering ability, strongest predicates. And that one there, just being metric, false. Because you can think about include all the x where false is the case. There's no value that can satisfy false. So in this case, it's simply just empty. So false is the strongest one. You just cannot, you just filter out everything, basically. Okay, question?
Shouldn't the relationship between the three sets be a strict subset rather than just a subset?
No, mathematically we don't really need to. But although in this case, yes, you can see the concrete example, yes, it does allow more. But I think when we say stronger and weaker, because we're going to use the implication sign to really say, right? So we can allow the equal sometimes.
But if both are equal, then how do you know which one is stronger and which one is the weaker if both cardinalities are the same?
So think about stronger, well, I think stronger and weaker, I think, yeah. Of course, there will be the case where you can say P is stronger than Q. At the same time, P is also weaker than Q. In that way, you will know that P and Q are just equal to each other. right? So think about when put it this way. When I say P is stronger than Q, I really just mean P implies Q. Whether or not they're equivalent to each other, I'm not sure. At least I can put P as antecedents. At the same time, if I also tell you that P is weaker than Q, in that way, Q also implies P. That will know logically they're equivalent to each other. Yeah, that's the way to put it. Yeah, it's a good question. Yeah.
I just have a question, like for a set equation like x such as true and x such as false, should true and false be in like the set, or is it just like some?
Oh, you can think about, you mean the true and false here, right? You mean here?
Yeah.
Right. So, we don't need to, because true, you can think about it's more like a constraint. So in the set comprehension notation, to the right of the vertical bar, you put a constraint. So usually we might put something like x larger than 0 or x maybe larger than 5, things like that. But true itself is already a predicate. That's just always true, despite the value for x, right? Good question. Yeah. All right, guys. So now the most important part for today. All right. Let's talk about guard strengthening. Okay. Once we go through the next page, you will be able to look at the proof obligation rule and then generate a sequence. That's all we're going to do. And then for the proof, you can go over there on the slides. I can also give you some highlights also on Tuesday. But you should definitely study that over the weekend, the proof itself. Now, refinements. When we talk about refinement, and we want to ask the question, why the guard strengthening should be the case. I'll talk about it. Why guard strengthening? Okay, let's recall very quickly. Let's say we got our abstract events, ML out. Okay, over there, we actually got the abstract guard G. Okay. Which is n less than d, right? Let's now spell it out. Okay, just abstract guard called G. And also we got the concrete one, ML out. ML out. That one is H. So that one is the concrete guard, concrete version. And if you recall, before the break, we actually figured out C equals 0 and also A plus B less than D, right? Something like that, right? So think about here, it's about M0. And over here, it's about M1. So now the guard strengthening proof obligation is trying to draw a connection between G and H. And see how these two guards should be related. The guard strengthening is saying the following, okay? The guard strengthening says it should be that H implies G. Which means H implies G. If you think about it, that means H should be stronger than G. So we are strengthening the guard in the concrete. So that's how you read it first. But I'm going to justify why this should be the case. Let me say that again. When you look at the abstract version of the guard and the concrete version of the guard for every event, the correct relation we want to prove would be the concrete guard should be stronger than the abstract guard. In that case, H implies G. All right? So let's now highlight this and then let's explain why it should be the case. Okay? The way to explain this is like this. Okay? Let me give you a principle. Okay? Intuitively, a refinement's behavior should be consistent with the abstract model's behavior. Okay, let me write it down. A refinement's behavior should be consistent with the abstract models behavior. So what we are saying is, you can think about here, refinements. That will be M1. The abstract model will be M0. Okay, what do I really mean by consistent? Consistent in the following sense. The refinement there, we take a more conservative approach. Refinement cannot create any behavior that's not allowed by the abstract already there. And then I'll show to you. No new behavior is introduced by the concrete events. Let's now visualize what's happening over here, all right? Let's say here, the way to justify this is like this. This is the correct way, right? Why don't we try to flip it and see why the other way is wrong? So it'll be easier for you to appreciate why the correct way, right? Why is it wrong? When you have G implies H, and just to remind you, the G here is the abstract guard. And the H over here is a concrete guard. Okay, let's see. So our diagram from before here is going to be very useful. Let's use this diagram here, right? If I somehow show the wrong way, let's now visualize it. I basically got G here, the abstract guard. And also I got H here, the concrete guard. Okay, so this is the abstract guard. And this will be the concrete guard. Right? And this one shows exactly that G implies H. So why is this wrong? Okay, so now if we are able to show this one here, let's take one here. What does this really mean? So this is a member that belongs to, that's going to make H true, but it's going to make G false, because it falls outside. Right? So that one there is going to show to us not G, but H. Let's try to interpret that. Not G means for this particular value there, the abstract event is disabled. Which means for this particular input scenario, the abstract in the abstract world, not this particular event is not going to happen, just disallowed for whatever reason. But here, H tells you that the concrete events, on the other hand, is enabled. Imagine this. Maybe in the abstract world, ML out is actually not allowed for some constraint. But suddenly, in the concrete world, when we do the refinement, somehow, suddenly for that particular restriction, it's not restricting anymore. So we can still allow ML out to go out. Okay? So let me just say, for example, for some value, ML out is disabled in M0, but enabled in M1. So this is what we consider as a new behavior, which is not acceptable. Let me try to recap, okay, just quickly. Okay. So what we're saying here is, when you look at each event, the abstract version and the concrete version, the abstract guard and also the concrete guard, the proof obligation about guard strengthening is saying that the concrete guard over here should imply the abstract guard. So that means this one here should be stronger. Okay? To really justify that, why don't we try to flip it and see why the other way is not correct. In that way, we're saying that if we got G implies H, that would mean we might have an input scenario right here that is going to satisfy the concrete but not satisfy the abstract. In that way, this concrete event will be enabled, but the abstract event will be disabled. So for the same input value, the concrete one is going to create some new behavior by allowing some event to just happen. Whereas in the abstract counterpart, you just don't allow that particular event to happen. Right? So think about this kind of justification here. Right? Question, or any part you're not exactly following. Okay? Could be a little bit heavy, so just try to grasp something here from this page here, just about stronger versus weaker, and also right here about the strengthening and also weakening. Okay? Okay. So that will be the final one. Okay, finally, okay, final part for today. So this will be the proof obligation rule for guard strengthening right here. All right? So that one there is telling you, in order for me to actually do guard strengthening, okay, I need to include axiom, abstract invariance, concrete invariance, concrete guard, and then abstract guard. Okay, already done. So this is the axiom. Why don't we try to work out one example right away? Okay. So one of the proof obligation will be, let's talk about ML out. And then we got guard strengthening right here. Okay, guard strengthening, GRD. Okay. So the first part is the axiom. And you can see the axiom simply, okay, I didn't include it here, but I'll write it down. So this is about the axiom. So we got D is a natural number. And also D larger than 0. So I'll write down the reference for you. You can also take a look. 0, 1. And also axiom 0, 2. All right. And then this one here is about abstract invariance right here. Abstract invariance are these two in the M0. N is a natural number. N less than or equal to D, right? Invariant 0, 1, invariant 0, 2, okay? And also we got the concrete invariance. Of course, to be complete, you got to include all of them, okay? I'll just write them out right here, right? All of them. So here I'm going to say A, natural number, B, natural number, C, natural number as well. And also A plus B plus C equals N. And also A equals 0 or C equals 0, right? And now this one here, let's isolate them. That is something we just discussed in the previous 2 pages. This one here is saying the concrete guard should imply the abstract guard. The index I over here is saying that when you are considering a particular event, if that event has separate guards, you got to prove them separately. For example, here we just got only one abstract guard. You can see we only got N less than D, so only one, so we don't have to. Okay, just one. Okay, so each abstract guard. Here we only got one, so that one's okay. Okay, so let's put the concrete guard first. The concrete guard right here, H, is going to be this one here, concrete. A plus B less than D, and also C equals 0. And then overall, we got the turnstile. And then we got, finally, the abstract guard, which will be right here, n less than d. Of course, the main thing we really are trying to do is this. The concrete guard entails the abstract guard. But in order to show that, we got to use all the different hypotheses. Any question just about this proof obligation here? The main parts, which is about the concrete implies the abstract, already explained, right, in the previous 2 pages. You can take a look, and then I can just do a recap again, maybe next week. But you definitely got to study for that. And then the next 2 pages, right? And then I'll tell you exactly what you study up to for written test 2. Okay? So we got 1 and 2. So the one we just finished over here is about the ML out guard. The slide has the answer, but you should really try as an exercise. Try it out, ML in guard. Okay, try to formulate it. Like that. Okay. All right, so next 2 pages, I try to list this sequence here, just for the one we just listed, right? That's the one for guard strengthening for ML out. And that is the one for ML in, right? These 2. So try to see if you can prove them. Again, I try to give you all the relevant inference rule right here already. Also, the solutions on the slides. But I would suggest you may, as a good practice, you may want to hide these 3, maybe, just to see which inference rule to use. Okay? And then I'll try to go over at least one of them with you again, maybe on Tuesday. But it's self-contained. You can also look at the slides. Questions? Okay. So for written test 2, I'm also going to announce that a little bit later to confirm. But I can tell you that you should really study until, okay, I'll tell you the slide number. One moment. Okay. Until slide 58. Okay. Okay. Okay, I'll put it here. For your written test 2, until slide 58. All right, that's it for today. If you got any question, I can stay longer to answer. Otherwise, I'll see you next week.